Okay, everybody. So can you hear me? Let me see. Okay, wonderful. So let's start. So I hope that everyone actually have a very smooth transition, right, from the kind of a physical learning to remote learning, and it somehow the COVID-19 is getting more and more worse, right? Kind of like most I would say you should find a way to entertain yourself, okay? Trying to find a way to stay safe, okay? Okay, let's start. So uh, today, that will be I think that will be the kind of a last lecture before the exam, right? We will have the exam starting from next week and the next lecture on Wednesday. So that will be a lecture we will review everything for the exam too. So today that will be the kind of the second to last lecture. Okay. So on Wednesday we will review all the codes and all the necessary stuffs you need to know for the exam too. But today we will cover something the last topic we in this book actually. So let's proceed to the slides. Uh, so previously, we spent like two lectures, right, on discrete optimization. Essentially, it's a kind of optimization problem that have a discrete variables, right? So that would be the discrete optimization. So the take-home message is have two messages. One is that discrete optimization is very hard to solve. And second is that different problems may have different algorithms. There's no general rules to solve the problems. So you may need to kind of like know a lot of algorithms to solve some problems. For example, in our lecture, we listed like 6 or 7 algorithms, right? So that we can tackle some optimizations. So today, we will switch gears to something new. So the problems, so we know how to make a problem very complex, right? So the previous one is trying to make the variables discrete, right? From the continuous to discrete. So the problem will, immediately becomes very hard. And then today, somehow there's another kind of perspective to make the problem complex. So sometimes complexity means kind of a more realism, right? The more complex problems is that actually the closer you are kind of getting into the real applications. So today, we're going to talk about another version of very hard optimization problem. It's called a multi-objective optimization problem. So from the name, you can see that this problem is actually have multiple objectives, right? So that would be let's say, this problem is very special because uh, we are not having a single objective. We have multiple one, right? So this is very common, in real world, right? So for example, you want to minimize your cost, right? At the same time, you want to maximize your revenue, something like this, right? That will be a multiple objective, right? Maybe in your project, you can find that. So mostly it's hard to define just a single objective, right? So mostly you will have multiple objectives. But so in most of time, you can ignore some of the objective, right? Just find the major objective. That's the way we can model the problem. But today, so we are going to talk about the problems that we have two or more objectives. All of the objectives are very important. So how to solve problem? How to solve the problem like this, right? So the problem is, for example, here. This is a very simple example. Okay, it's a kind of a makeup example, right? I kind of create this example so that you can see we have two objectives. So you can see that these objectives, these functions are pretty simple, right? The function one and function two, they are two objectives, and both are quadratic. So these are two very simple examples of a multi-objective problems. And for most problems, we know that they are kind of they have constraints, right? For example, here we have a simple constraint that the x, y, they have a range, right? Have upper and lower bounds. So that would be the problem for this kind of examples. So of course, in your project or in many real applications, you can formulate your problem in this way. So pretty much that you have multiple objectives. So for example, F1, F2, or many others. So we just use this example to illustrate how to solve the problems, right? Multi-objective optimization problem. So this kind of problem is very kind of special because it has multiple objectives, right? So how to solve this kind of problem? Any idea? Or if given this kind of things, right? Very simple one. We have two objectives. So can you give me one solution, X and Y, that is very good for both objective, right? So that would be something like this, right? So how to solve a multiple objectives? One and one, yeah, that would be, yeah. So I think Jamie says that we can have one to one, right? Which is very good for the partial, yeah. So yeah, I think Jason is talking about just partial objective, right? So we can ignore some of the objective. For example, for Gemini, so if the solution is one and one, so pretty much is that we one and one, we can see that that's the best solution for the second objective, right? F2, that's one and one. But for the first objective, that would be 0 and 0, right? So it's somehow you need to do some trade-off or some kind of balance, right, between these two objectives. So there are actually not many solutions or many algorithms to solve it, very limited. So as far as I know, there are about 3, but today we only cover about 2 algorithms. So actually the third one is more complicated, but I don't think it's really kind of useful. So the commonly used algorithms are 2 methods or kind of 2 algorithms. They are using they are used to solve the kind of problems. I think some of you already touched some kind of key things about problem, right? So because we have 2 objectives, so you have to think about some trade-off, some balance between them, right? So you can see from the first one, the weighted sum. So maybe from the title of this kind of thing, you can know that, right? It's kind of like, it's okay to have multiple objectives, but so for our commonly used algorithms, we can only handle one objective. So the way to convert multiple objective problems is pretty much that to do the kind of a weighted sum of the 2 objectives, right? So for example here, we know that we have F1 and F2, that will be 2 objectives, but we can actually have a kind of a weighted sum, right? So the idea is that we can have alpha. So alpha will be a value that's ranges from 0 and 1, right? So let me just use the pointer example here, the laser pointer. So alpha, that would be some value from 0 to 1. For example, very fair weight, that would be 0.5, right? So I have half percentage of the weight come to the goes to the F1, right? And another half goes to the F2. So pretty much that I just average the 2 weights, correct? So that would be a way to combine different objectives together. So just simply weight kind of which is some of them. So something like this, right? The table here shows that if you have, for example, if you have a different weight, for example, each row represents one specific weight. For example, the first row, alpha equal to 0, right? So if alpha equals to 0, which means the F1, this term, is kind of like 0, right? So we don't consider F1. So pretty much that we only have F2. So in that case, our best solution or our optimal solution, that would be 1 to 1, right? So which is Jimmy talking about, right? Pretty much that you have 1 to 1, and then if you plug in 1 to 1 there, right, you can evaluate the kind of the function, right, of objectives here. So if you have 1 and 1, then the second objective will have 0 value, right, which is optimal. But for the first one, right, for the first function, that will be the 3, right, which is somehow a little bit large, right? So that's the first case. If we have alpha equal to 0, which means F2 will occupy or dominate the whole things, right? That would be the kind of the one case, right? We just ignore the first objective. So another extreme situation is the alpha equals to 1, right? Correct? If you look at the very bottom, the bottom row, so which means the alpha equals to 1. In that case, if alpha equals to 1, you can see that the second term, right? The second objective is kind of ignored, right? Because it's 0. Then we only need to minimize the first objective, right? So in that case, so we can see that this is because alpha equal to 1, then this term is kind of eliminated. We only have the first term. For the first term here, we know that the best solution or the optimum solution that will be 1 and 0 and 0, right? In that case, we can see this is a solution. And F1, the value will be 0. But for F2, the value will be 3, right? It's kind of like large. And then that would be a very too extreme situation, right? So you don't actually, for us, if we are faced with this kind of two objectives, so we don't want to go to the extreme situation. So what we want to do, probably we want to go to like a 0. The alpha equals to, for example, 0.5. How about this, right? So that would be kind of fair, right? So that you can see that all the objectives, they have the same kind of object value, right? It's just by identical that I don't know, they are identical for this one, right? So because we kind of give them the same or just a fair consideration for each objective. Actually, if you, so for alpha, you can go 0, 0.5 or 1. Besides that, you can go many others. So for example, you can go 0.1. So which means that if alpha equals 0.1, means that you have 10% consideration for the first objective, right? In that case, your solution somehow is also very close to the the majority of the consideration goes to the second objective, right? So which means you can see that the solution is still very close to the kind of solution for the second objective only, right? When you gradually increase the alpha, right, from 0.1 to for example, 0.9, you can see that the kind of objective is gradually, favor the first objective, right? So you can see this is a way to interpret the weight. So it's something like you are adding different ratio for the objective, right? If alpha, something like this, right, equals to 0, means you don't consider it. If you put 1 here, you consider it only, right? So that would be a way to couple different objectives. So clear, right? I think this kind of a weighted sum should be very straightforward, right? I think most of you can think of this kind of methods, correct? It should be clear, right? I hope everybody say yes, right? You are clear, right? That's good. a question for you here. How do we pick the weight alpha? Let me see, should I give this? How do we pick the alpha? Okay, Dylan says we can based on the desired effect to pick the alpha, right? Or we can allocate weights based on importance. Yeah, that's a very good way actually. It's very true. I think that's it's very subjective. So you can, there's no like a golden rule, or there's no kind of guidance to pick the alpha. So it's purely based on the domain knowledge. So you can see that if the first objective is more important, then you can pick the alpha, right? Kind of larger than that one. That's the general rule is that something like this, right? Depends on their kind of importance, or kind of like, because weight means importance, right? So if you think that this guy is important, okay, here goes another question. So from Achana says, don't we try all weights? Your slide says that all values from 0 to 1. That's very true. So here I tried all different weights, right? So, but the question is that for different weights, for example, alpha equals 1, you will have one solution, right? The decision will be 1, 1. And for the second alpha, you have another solution. And for the alpha equals 1, you have a very different solution. So essentially, you have to make a decision, right? What kind of x and y should be, right? You can only pick one. So which one you should pick, right? We can of course try all of them, but essentially, or other than, at last we have to pick one solutions, right? So which one you want to pick? So that's the question. It's very true that we can try all of them, and then we can analyze, for example, one-to-one, we can analyze all the solutions, trying to figure out whether a solution makes sense or not. Maybe you have some other criteria to pick them, right? So I think, Achana, you want to say that, can we generate all different alphas, and then we have a list or a set of different solutions, right, at hand. So all these solutions are pretty good. So, but we want to use some other criteria or some other methods to kind of pick one of them. I think that's also a very good way. So we'll cover this later. So actually, this set has a very fancy name. So you can see that, oh, let me put the laser pointer. You can see here, this is a kind of a set of a lot of solutions, right? At least here, we have 11 solutions. So these solutions, they form a set. So the collection of this solution has a very fancy name. So we'll talk about that later. Pretty much is talk about the Pareto frontier. But the thing is that any solution from this list is very good. Depends, they're pretty good, but you have to pick one of them. Maybe you can use other criteria or some very fair one, or kind of a conservation one, is that you can pick 0.5, something like this. Okay. So that would be a way to pick the alpha. But it seems that this methods somehow, this weighted sum somehow is not that good sometimes, because you can see that for alpha, the weight, if you pick weight equal to 5, right? So you are assuming that F1 and F2, they are kind of have the same importance, correct? If you pick alpha equal to 0.5. So you are assuming that, or you are hoping that F1, F2, they are kind of have the equal importance. But this is not the, this is not always the case. So for example, F1 and F2, they may have very different units. Okay, so for example, let's talk about in money. So F1, for example, we are formulates F1 in the money of how many billions, right? So for example, 1 means 1 billion, right? That would be 1. But for F2, we are using dollars. For example, just $10 or $100, right? So you can see that even though if you give 0.5, right, you will generate something a similar solution, right? Kind of like just 1 and 1, but because the different objective have very different units or very different kind of way to I would say different meaning, right? So even though they have the same value or somehow a comparable value, but their units are very different. In that case, actually, it's very unfair, correct? So in that case, everybody knows what I'm talking about, right? Because the challenge is that even if you assign alpha equal to 0.5, there will be the case that because F1 and F2, they have a different unit, then it still will be unfair, or somehow it's kind of a very kind of a biased solution, right? So any ideas of how to figure or how to solve this kind of problems? So the F1 and the F2, they have a very different which means they are not comparable at all. So how do you pick the alpha, or how to any idea or any solutions to address this kind of a problem that F1 and F2, they are not comparable at all? They may have a very different unit. Any idea? Yeah, so I think Dylan says that converts units to a like unit. That's the way actually. So a constant that releases both units. That's correct. So it's true. So I think a better way is not really weighted their absolute value, right? We want to weight their kind of a relative value. So for example here, so for F1, we can actually divide it by some kind of a normal number, right? For example, we can give a starting solution, for example, x0, y0, right? Give it some like a typical number. And then we can use F1 divided by that number. Then we can have a kind of like a unitless value, correct? It's called a unitless. So pretty much that it's a relative value, right? So that would be a fair consideration. So which means we're not really weighted their absolute value, but actually we are converting this value by dividing a normal objective. Also for F2, we do the similar things. In that case, their a unit will be kind of cancelled, right? So then that would be a unitless, a kind of a combination. So that would be kind of fair enough to consider that, right? So I think, hold on, we don't have homework for this, I think. Yeah, I think we don't have homework for this week. That's fine, so we don't do any exercise, but I hope that you can see the idea is that if the F1, F2, they have a very, very different unit, we can actually, convert them to a relative value. Okay, so that gives us some comparable weighted up. So actually that kind of methods is the third one. So there's a kind of one very systematic way to cancel this kind of a unit effect. But I don't think that's very meaningful. So but, for us, we only need to know that F1 and F2, they should be in a range that they should have the similar kind of order at least. For example, F1 will be, kind of 5, then F2 should be like 2 or 3. You cannot be 200 or 2000, something like this, right? That would be very unfair. Okay, so That's the way we do this, correct? This is the first method, which is very intuitive. So another one is somehow, I think, is also a kind of an intuitive method. So we can, the idea is that it's okay, we have multiple objectives, right? F1 and F2, but for us, we only know how to solve one objective or single objective problem, right? So in this case, we need to, solve or kind of convert another objective into something else, right? For example, here, so we have only left F1, but for F2, we are not considering it in the objective. We actually put it in the kind of constraint, right? So the essential idea is that for F2, we know it's an objective, right? We know there are some value about it. But how about, let's just give you some kind of bounds, right? We call it epsilon, right? It's kind of a bound, right? So as long as your solution for objective 2 is smaller than some value, which is a kind of a threshold, right? As long as this objective is somehow within control, then we are kind of happy about it. For example, if F1 represents the kind of a revenue, F2 represents the cost. How about this? Or there are some other ways. For example, F2 will be the cost, F1 will be the performance. How about this, right? So we want our performance to be, oh, it's not performance. Anyway, but there's some kind of objective we want to minimize. But for the cost F2, we hope that it should be within some kind of a budget, correct? As long as F2 is within control, then we are happy. Then we can solve the F1 problems, or we can solve the first objective, correct? So everybody clear about this idea, right? So in essential idea is that it's okay to have multiple objectives, and then we can convert most of them, right? For example, here we can convert the second objective into a constraint, so that as long as this objective is acceptable, right? So that we are happy about it. For example, here, if the F2 means cost, then as long as the cost is within some budget, then we are okay for your decision. And decision within this kind of budget, we approve it, correct? So that would be the another way to handle this kind of multi-objective problems. But here comes the same problem or same kind of challenge for the previous methods, right? How do you pick this kind of epsilon, right? So for here, in this table, I actually listed a set of different kind of a value, right? So from 0 to 3. So let's just take these numbers for granted. Let's say we have this kind of different, we try different epsilon, right? For example, we tried a epsilon equals to 0. If epsilon equal to 0, what does it mean? If we look at the function, right? The function f2 is a quadratic function, right? So the minimal is 0. If we say that f2 should be equal or smaller than 0, pretty much means we only have one solution for this constraint, right? X equal to 1 or 1, right? So which means we only have one solution, pretty much, right? And you can see that f2 is, of course, satisfied the kind of constraint, right? And also our f1 is somehow 3, right? There's no other options or other kind of way. There's only one solution, right? Only one feasible solution. But what if for epsilon, we don't really have a a very restrictive requirement? How about let's just relax, right? How about let's just increase our budget or increase this kind of epsilon a little bit, for example, by 0.5, right? Then you can see that if we increase the point by 0.5, so we have a lot of solutions, right? If you look at the kind of F2, if you look at this F2 objective, so there's many actually infinite solutions that can have the objective that's smaller than 0.5, right? So we can see a lot of solutions exist. And then we can actually, within this kind of constraint, we can solve or we can minimize the first objective, right? So we know how to solve this problem, right? This is kind of constrained optimization, correct? So, and also it's very simple because it's continuous, right? So we can use MATLAB. So I will show you this, how to solve this kind of things, right? So pretty much that when we increase some kind of a threshold, so we have a lot of solutions, and this solution is kind of a gradually favor the F1, right? You can see the F1, the value actually is kind of a dramatically reduced, right, compared with 3, correct? If we further increase the threshold, right, which means that our constraint or our objective F2, we don't require a very optimal solution, right? We just say 1 is okay for us. The cost 1 is okay for us. Then what we want to do is that you can see that the F1, the first objective is further minimized, correct? If we continually increase or relax the threshold for the second objective, for example, if we increase to 3, so what happened is, if we increase the threshold into 3, so actually we can get a solution that's pretty much the optimal solution for F1, right? So pretty much that for F1, we know F1 is a quadratic, right? Like this. So X and Y, if it's 0 and 0, which means is optimal for this objective only, correct? So in that case, if our epsilon or our constraints, this kind of epsilon value is somehow increased to 3, then actually our solution is pretty much optimized for the first objective, correct? So you can say by changing the threshold, we may have different solutions, right? And again, we can get another set of or another collection of the optimal solutions, correct? This is also very good. But again, here comes another question. So how do you pick the epsilon, right? So for this, actually, I already list or already kind of show you the methods, right? How to pick the range of epsilon. So essentially that there's some way to do this. For example, for epsilon, you can do one thing. For example, you can just ignore the first objective, right? You just minimize the second objective given the previous constraints, okay? So which means we don't consider F1. We just trying to minimize the second objective, right? So for example here, in this example, we ignore the first objective, then we just minimize the second objective. So what will happen is that if we don't consider the first objective, then the best value for F2, that would be kind of 0, right? Then the solution will be 1, 1. So for here, we can know the starting point of the epsilon, right? That would be the optimal solution for the F2, correct? Only. So if we only minimize the second objective, then we can get the starting point for the epsilon 0, correct? And then if you want to know in what kind of order or magnitude should the epsilon goes, right? For here, because I know the problem, I try a lot of epsilon, so I can know 3. But actually, maybe a better way is that you can sample XY for different samples, right? Have a kind of just randomly sample them, and then get some kind of evaluation for F2. Then you can get this kind of range. Then if you get this range, you can evaluate, kind of a different epsilons, right? And then get some sense of the collection of optimal solution, correct? Good. But again, so if we want to connect this kind of epsilon into the kind of real world problems, right? So what do you think that would be a good way to pick the epsilon? Or we know that we have 3, or we have a set of different epsilon, right? Ranging from 0 to 3. but in in reality or in practice, we have to pick one, right? So which kind of a solution you want to pick? Any insights or any kind of suggestions that if this is a problem, right? You have two objectives, and then you want to use this kind of a epsilon constraint method to solve it. But what's the value for the epsilon? You think it's good? Uh, Worst case scenario? You mean Yuri says worst case? We don't want worst case actually. So it's again, I already mentioned that, right? Epsilon is actually related to some resource or related to some kind of physical constraints, right? So mostly epsilon has some physical meaning of it, right? So for example, if F2 will be the cost, then we have some kind of budget, right? So that would be the budget. Or if F2 is related to some performance or some kind of index, then we will have some like a minimal or maximal requirement, right? So when you design something, right, there will be some kind of a kind of a minimal or some kind of bounds for the performance, right, for the objective. Then you can put that kind of bounds into here. So that would be the kind of the way to connect or use the domain knowledge to pick the epsilon. So is that correct? So for example, so there's maybe we can use another example. So remember our the what's that problem? It's called so we have a swimmer, right? So we have a kind of lifeguard. We want to, so if some swimmer in the ocean that somehow get into trouble, right? So our lifeguard trying to save him, right? So he wants to make a decision where to, because there's the sand and water, right, in between him and the swimmer. So he has to make a decision where to, jump into the water, correct? So in that problem, our objective one, that will be the total time, right? So we want to the lifeguard to reach to the swimmer as soon as possible, correct? So that's the first objective. We hope that time should be minimized. But actually, there are some other kind of objective. So for example, so we, because this is kind of life saving stuff, right? So we hope that this kind of a lifeguard will spend very minimal efforts or very minimal energy trying to, swim or trying to reach that guy, right? Because we want to save the energy, to save the, to save the lifeguard's energy so that he can have enough energy to carry the kind of swimmer, right? So this is kind of one example. So which means we have a second objective, which that is trying to minimize the total energy of it, correct? So in this case, if we want to use epsilon constraints to solve it, then for the second objective, the kind of energy saving rate, we want to minimize the total energy to solve it. But actually, we have some kind of a threshold for that energy, right? As long as, for example, as long as the kind of traveling or swimming from that for that distance is within like a 10% of the total energy, then we're good, correct? So something like this, we can actually convert the objective, we can tie it into the kind of a real world, a kind of a constraints, right? Somehow, because mostly for the objective, it means that we have some expectation for this objective, right? Or we can use that expectation to pick the epsilon. Okay, so that would be the way to solve this. Okay, so that's how do we pick the epsilon based on our domain knowledge. Good. I think that would be the two methods, or I think we can stop if we only want to know how to solve the multi-objective optimization problem. So actually, we have these two methods, which is we know it's very intuitive, but that's very useful mostly. So you can solve the multi-objective problems by either combining the objective together or convert one objective into the constraints. Okay, so that will be the two ways to solve it. So again, we can start. So you can leave now if you think that you only want to know how to solve it. It seems that all of you want to know what happened next, right? So we still have about like half an hour. So in the second part, so we're trying to explore more about a multi-objective problems. So to solve a multi-objective problem is somehow pretty easy, right? We have this kind of two very practical methods to solve it. But for multi-objective optimization, actually there are many more things that we want to explore. So for example here, let me show you something. So for weighted sum, so again, I think Achana mentioned a very good point that we can try all of the different weight, right? And then we can get, see that this kind of column, it's 11 solutions, right? It's a collection of the solutions, right? And also we can get a collection of the objective, correct? F1, F2. For different solution, we'll get different objectives, right? And the thing is that, what if we plot, kind of like from here to here, right? So we plot the F2 versus F1. You can see that this graph actually shows a comparison, right? You can see that each point, for example, this point is 0, 3, that actually this point, right? 0, 3. And also we have some 3, 0, that would be this one. So if we plot the objectives, right, here, it looks like something like this, right? So actually, if we proceed, you can see we can use the kind of very smooth curve to connect them, correct? Very interesting, right? So when we kind of, increasing the alpha, so when alpha equals to 0, pretty much that we get this point, right? Then when we gradually increase the alpha, so pretty much that the solution will be kind of gradually shift to this one, right? Very interesting, correct? Then we have a much more interesting thing is for our second method, right? We're using epsilon constraints. For the second method, you can see that we can pick the different epsilon and generate different objective, pairs, right? And if we plot, 3, you can see that, right? We can plot all the stops here, right? This is another plotting, right? We can, for example, here 3, 0 means the epsilon will equals to 1 or will equals to 0, right? Then we have this kind of objective position. Then by increasing the epsilon, the threshold, our kind of our optimal or our objectives are gradually shift to this kind of a position, correct? So very interesting that we can use another curve to describe it. But you may already observe that these two curves actually they are identical, right? Correct? Very interesting, right? We use very, very different methods, but we get the same kind of curve, right? Any idea of this? How do we? Yes, right? Pretty much that. This curve is very interesting, right? It's I would say all the points on this curve that will be optimal, right? And also it will correspond to some epsilon or to some kind of alpha, right? It's very interesting. So the idea is that this kind of a curve, somehow they have a very unique name. This is called the Pareto frontier. Okay, it seems that my slides is not really well organized because here we jump to another kind of issue. It's called how to visualize. Uh, okay, let's just pause the kind of idea of here, right? So I just want to know that these two methods, they generate the same collection of solutions, right? Although they are very, kind of radically different, but it seems that they can generate the same collection of solutions, right? So let's just pause this kind of topic for a moment, and we'll get back later. We'll get back to this kind of topic later, okay? So let's just to change to something else. This problem is called how to visualize the multi-objective optimization problem. So yeah, already listed here, right? So the first idea that would be, we just kind of visualize the objective individually, right? So just like our, very normal methods, right? We just, list kind of plot the curve, right? Kind of a 3D curve or contour or something like this, right? So for the surface. So we have a bunch of tools to visualize the single objective problem, right? So pretty much that is contour plotting, right? So we can plot the contour for each objective and get the sense of the problems, right? So that's the one way to do it. But for this kind of multi-objective problems, we have a very different, very useful visualization methods. It's called objective space. So here's the idea. We have this example, right? We have two objectives, F1, F2. And then this kind of function, they have, two constraints. Then you can see here, on the left side, left hand, you can see it's called decision space. So the horizontal axis represents X, right? And the vertical one is Y. So pretty much you can see this is the X and Y. And then because our, there's a range for the XY, right? So pretty much that this is a -2 and I probably made some mistake here. That should be -2 and 4. I will change that. Pretty much is that -2 +4, okay? That would be the range, okay? This is a range for the decision space, okay? And then we can sample this kind of a decision space. For example, we generate 4x4 different solutions, right? Different samples. And then we can evaluate each samples. For example, we can evaluate this kind of 0, 0, 1, right? That would be our kind of a very simple solution, right? X equal to 0, Y equals to 0. What happened is, if you plug 0, 0 into the two objective, you will get F1 and F2, right? For example, for F1, that would be because XY equals to both equals to 0, then this guy F1 will be 0, correct? And F2, that would be 1 plus 2, that would be 3, right? So which means you look at here, on the right hand, it's another kind of plot. So the horizontal one will be the F1, the first objective value, okay? The vertical axis represents the second objective value. And in the case of x equal to 0, y equals to 0, you can see that we actually we generate 1 point here, right? This is 0, 3, correct? Okay. Then for other points, for example, 2, we can generate another kind of objective pair, right? Then pretty much that we can evaluate all the sampled solutions, right? And then we can plot in the objective plot, right? So the objective, this kind of plot is called objective space plot. So which means that every point, it represents the kind of X represents the F1, the first objective value. The Y represents the F2, the second objective value. Okay, so that would be the way to construct the kind of objective space. For now, we have a very sparse sampling, right? So how about let's just increase the density of the samples, right? For example, here we have generated like maybe 20 by 20 different samples, right? And then we can also evaluate the different points, correct? You see that? And of course, we can continue, right? So, which is very fully dense, right? Pretty much every point is sampled. Then we can generate some kind of like this curve, right? So all the kind of red region represents the, objective space. Okay, everybody is clear about the objective space. So, right? So what does one point here represents, right? So for each point in this plot represents one solution's objective pairs, okay? For example, here probably represents the x object, the first objective and second objective, right? We will construct one point here. Because this is critical. So I hope that everybody can, if you have a question, you can ask later. But yeah, I hope that for now, everybody can get a sense of the objective space, right? So pretty much that, so the point, each point on this graph represents the kind of objective pair, right? Because for multi-objective, we have at least two objectives, right? We can select one pair of them and then plot here, right? So in this way, we can get a kind of, plotting for it, right? So that would be something like this, okay? So that would be the visualization for this kind of a multi-objectives. Okay, you said that we jump to another topic. So I will show you actually all the topic, they were connected. So we will connect them, at the end of this kind of lecture. But for now, let's just, please just bear me that we introduce a topic like, kind of a very randomly. But let's talk about another kind of things. You talk about the goodness of solutions, right? So for here, the very fundamental question is, give you two solutions. How do you say one solution is better than another one, right? How do we say this? So for single objective problem, that could be very easy, right? Because we have one objective, then we just directly compare the objective of solution one and that of solution two, right? If the solution one has a smaller objective, then it's better, correct? So that would be the one or single objective for problems. But how about this kind of a multiple? You have two objectives, right? You have a multiple criteria, right? How do you, kind of judge, or how do you compare the different solutions? Any idea of it? If you have two solutions? Okay, it seems that it's very hard, right? So for example here, the same example, right? We have two solutions. For example, x equal to 0, y equal to 0. And we have another solution. So 0 and 1, correct? That's very different solutions. And then for solution 1, we have f1 equal to 3, f1 equal to 0, and f2 equal to 3, right? You can see that this kind of things, they are very different, right? This is a 0, 3, but for the second solution, 0, 1, we have another kind of objective, right? It's 1, 1. If you compare these two solutions, pretty much it's very hard to say which one is better, right? So which one you think is better for 1 or 2? You think that is better? 2, why 2? James, why 2? It's kind of a balance, right? You think? Yeah, so somehow if you are talking about f1 plus f2 is smaller, right? You are talking about their weighted sum, right? You think that we have kind of, half of the consideration goes to F1, half goes to F2. So that would be, if the weight that would be 0.5, then in that context, then this solution is better. But what if we think that the F2, the second objective, is much more important, right? F1 is not important, right? So how do you think that in that case, maybe first solution is better, right? So actually, here's a kind of a, very hard kind of aspect of this kind of a problem is, for multi-objective, it's very hard to say which one is better, right? So something like this, for solution 1, solution 2, they are actually, none of them is better than another one, because you cannot say, because you don't know which kind of objective is more important, right? So you cannot say which one is better. So that's something like, for these two solutions, the only thing we can say is that both are very good, okay? And so to compare them, actually there's a very fancy way to say better. It's called a dominance, okay? Dominance, it means that, for example, if solution 1 dominates solution 2, it means that solution 1 is completely better than solution 2, which means that all the objective of solution 1 is smaller than the objective of solution 2, right? Which means no matter which objective we are comparing, that solution 1 is better. Then in that case, we can say solution 1 dominates solution 2, which means solution 1 is much better, right? So for example here, we say, if we compare solution 1 and 2, right? If we compare this kind of a solution 1 and solution 2, right? And in this graph, so it's an objective space, right? We previously defined the objective space. So the horizontal one will be F1. We want to minimize. The vertical axis also we want to minimize the second and the objective, right? So that's, which means that the smaller the better. So if you look at this kind of a graph, so we can see that the solution 2 is better than solution 1, correct? Correct. Then, so in this case, we can see that solution 2 is better, because no matter which or what objective you are trying to compare, is much better, right? Or at least, no worse than it. So now we say solution 2 is better. For example, if we compare solution 2 and 3, again, solution 2 wins, right? Because, it's smaller than some, at least, there's no way for solution 3 is kind of can compete the solution 2, right? Because from every aspect, solution 2 is better. Also, if we compare solution 4 and 5, you can see that this guy is better, right? Or 4 and 3 is better. But if you compare solution 2 and solution 4, right? That's tricky part. We cannot say solution 2 somehow is better than solution 4, right? Because if you look at compare this 2 and 4, if you focus on the first F1 objective, right, then you can say solution 2 somehow is better, right, smaller. But if you focus on the second objective, then solution 4 is better, right? So in this case, solution 2 and 4, we could only say that both are very good solutions, and along with them, they cannot dominate another one. So in this case, we have a special term for it. It's called long dominated, which means 2 and 4 are both very good. Okay, so this is called dominance. And this actually comes back to everything here. So for example, our problem is, if we pick one kind of a solutions objective right here, so which means maybe there is kind of 0, something like 3, something like this, right? So for this point, we call it long dominant solution, because there's no solution that could dominate this kind of things, right? Because this is kind of at the boundary of this kind of, very good solutions, right? Unless you have a solution that is something in this area, then we can say this solution is not really non-dominated. But for now, there's no solution from the red region can completely better than this solution, right? So which means this solution is good, right? Somehow, at least it has some strength, correct? So that's the kind of key things for the non-dominated solution. It must have something that is very optimal. Okay, there's no solution could completely, beat this kind of a solution. Okay, that's the idea of this. And actually, we can list a lot of them. This, right? This. How about this? So I also list kind of a different colors, right? You may know something like this, right? Are these solutions long-dominated? No, right? I think we have very good answer. For example, for this kind of for this branch, right? 1, 2, 3, for this kind of things, right? So these solutions, right, can dominate all of them, right? Because no matter which objective you are trying to compare, this solution is better than all of them, right? So which means there exists some solutions that can completely better than this solution, right? Which is not good. So how about this, right? For this kind of side, the three solutions. For these three solutions, you can see that these kind of solutions can dominate all of them. So which means they are kind of not really optimal. So the only thing left here is this kind of boundary, right? This kind of thing is called, you can see that we can actually figure out all the solutions here. It's called the Pareto frontier. Okay, so that's a very fancy name. Pareto is kind of a famous mathematician, kind of economist. So pretty much that he somehow figure out this kind of term is called the Pareto frontier, which means that it's a collection of solutions that every solutions, I would say, let me see, any solutions in this kind of a frontier is non-dominated, which means if you pick any of them, then pretty much you are kind of confident that it's somehow optimal. Okay, there's no way that you can find another solution that is completely better than it. Okay, so that's the meaning of non-dominated, which means that any solution in here is good solution. Okay, because this is very different from solution like in here or here, right? Because they are not very good, because you can pick some solution that is completely better than it. Okay, so that would be, this is called the Pareto solutions. And let's come back to our very first topic, right? Our very first topic that we generate some kind of see that? We generate some kind of solutions here, right? If you look at this kind of a green color plotted point, right? Which is I plotted all the solutions here. That's 11 solutions. What happened here? Anyone can describe what happened here? Yeah, that's true, right? We found the frontier, correct, right? That's a kind of a very kind of magic. So we know that these solutions, the two methods, they're pretty simple, right? They're pretty intuitive, but it's very powerful. By adjusting the alpha from 0 to 1, we actually find all the solutions in the frontier. Okay, so that's a very kind of a crazy, right? So because you can find all the non-dominated solutions, right, which is a Pareto frontier, right? And then just by simply use the weighted sum. And also, again, for the second methods, epsilon constraints, the same idea, right? Same story. We pretty much, here I plot all the solutions here, right? It's again, it's in the frontier, right, of this kind of all the solutions, correct? So from this perspective, actually, you may know the meaning of the frontier, right? Frontier means is actually at the front right? The front line of all the solutions, right? If you want to pick some solution, then you have to pick something here, right? Because they are very good, right? All of the solutions are very good. You can pick any of them, and they are pretty good solutions. Okay, so I hope that by at this point we already connect everything, right? So the first thing that we want to visualize the objective in a kind of objective space, right? In that case, a pair of objectives actually are plotted against with each other, right? And then you can see that each point in this kind of plot represents one pair of objectives, right? You pretty much represent one solution with, and that's number one. We want to visualize them. Number two is that we can use this kind of weighted or epsilon constraints method to solve some optimal solutions. And we can get a collection of different solutions. And all the solutions, actually, they are the boundary or at the frontier of the solution, right? This is called, what we say, the Pareto frontier, correct? So in this way, we actually connect everything together, correct? So hopefully this can give you some kind of idea of multi-objective solutions. So the idea for this kind of thing is multi-objective is somehow very simple to, I shouldn't say simple, but at least we have very intuitive algorithm to solve it, right? As we say, we have two methods. One is to combine them, right, by kind of weighted sum. Another one is kind of like convert one objective into the kind of constraints, right? These are two very straightforward methods, but both methods, they can actually find the frontiers, okay? So that's a very unique kind of a property for multi-objective optimization problem. Is basically you have a collection of solutions rather than a single one, okay? Because it's multi-objective, which means you may have different weight or different consideration, then you can have different totally different solutions. But all the solutions are non-dominated, which means they are very good, and you cannot find a solution that is completely better than this. Okay, so that will be the kind of all the things for this lecture. We still have about 7 minutes, so I'm trying to give you a kind of a MATLAB demo, okay, to show how to find this kind of frontier, right? How to solve this kind of things and how to visualize this kind of frontier, okay? Pretty much is how to generate this kind of a graph. Let's do that, and after that, so this lecture is done, okay? Let me just open this. So can you see my MATLAB? Good, wonderful. I need to locate the position. Should be, give me 1 second. Oops. Okay. I think that would be something like this. This is a very, let me just try to run it to see what happened. Oh, you can see it's, so this is a way to generate a, oh, no, that's very complex. So this is a way to generate the frontier, right? So you can see that each point is pretty much the optimal solution corresponding to one weight or one epsilon, okay? Let's say, probably I want to simplify this kind of solution. Yeah. Okay, so let's see. we can actually debug this kind of a file, right? Let's run this file one by one. So from here, as usual, right, we defined the objective function, but here is we have two different objectives, right? F1 and F2, correct? F1 will be quadratic, F2 will be another quadratic, and it has mean optimal from 1 to 1, right? And our range, that will be -2 to 4, right? So both x, y, they are kind of symmetry. Okay, then at this point, we're trying to, this is trying to generate the first, oh my goodness. Let me just run through it. So this chunk of code, they are trying to plot the the objective space, okay? Because I sample some x. Let's run through it. You can see here, this is some graph I showed you, right? So we have a kind of a 4 by 4 samples in the XY space. And then for each kind of point, we actually evaluate its objectives, right? And then we can have another plot, the F1 versus F2, right? So that would be the objective space plotting, correct? And then if we go to dance, right? Here we see dance, then let's run through it. But maybe you can see the comments. They're pretty. You can do this. So firstly, we sample the points, right? And use the mesh grid, we can sample a lot of points. And then we plot this kind of sample points on the left side, which is x and y. And then we can, here, we can evaluate the kind of x and y, right? So we can generate another kind of, so probably, yes, let me just, seems this is the previous one, and then we can generate another one, right? You can see this is a frontier, right? But it seems that, oh, this is the range is wrong, right? So that's because I'm actually doing multiple things. Give me 1 second so that I can show you what happened. So this is if we have a dense sampling, okay? If we have a dense sampling, then you can see that x and y, we have a lot of samples, right? And then we evaluate all samples, and then we can have a kind of a sampled objective space, right? You can see that this is the frontier, right? Camera frontier, right? So at this kind of a tip, that all solutions are good solutions, okay? But these are very bad, right? Because we can have some solutions that is completely better than it, okay? So that's something we call it frontier here. And I think probably let me just clear this code for you for a moment. Let me just clear this kind of things. And then let's see, how do we find the frontier, right? So for here, we have, it's called weighted sum, you can see. Let's run through it. So for the weighted sum, you can see that the code is pretty light. So, which means we don't need too many codes. Oh, there's no battery. Hopefully we can get through this. So you can see here, I have a for loop so that I can evaluate, for example here, I can evaluate all the alpha from 0 to 1, okay? Then for example here, I generate alpha that is 0, okay? And then for this alpha, because this is a weighted sum, right? So pretty much that we have alpha times the first objective and 1 minus alpha times another objective, right? By trying to, kind of a weighted sum of these kind of two objectives within one objective, right? And then I'm using our old friend, which is F-mean search, right? So we formulate this kind of a two objective into a single objective. And then we use the fmin search to start to search the solutions, right? And if, let's say, after we search it, so it comes to our solution, right? Which is 1 to 1, right? So which means if alpha equal to 0, which means we have, the F1 is ignored, right? We only have the F2 solutions, correct? Give me 1 second to plug the battery. I don't want to lose everything. Just 1 second. Okay. So, and then we use this kind of things to, record all the non-dominated solution. Okay, this is 1. Then at this moment, this is empty. Then if I run it, I have a 1 row added to here, right? And then let me just run through it. I have another alpha equals 0.1, right? That's another one. Then I can get a solution, which is this, right? So pretty much that, because alpha is dynamically changed, then we can have a different, kind of objective, right? Then we can solve this problem like this. Then when I run through it, I can have another solution, right? You can see that this, we already have 2 rows, right? They have, or 2 columns of this kind of, which means we have 2 non-dominated solution, right? Because based on our analysis, right? So for different alpha, it will generate different non-dominated solution, right? Because for each alpha, we're trying to minimize the kind of a combined objective. Then the generated solution will be non-dominated. Okay, so by running this kind of a for loop, we can find, if you want to, let me go up. So we can find 11. You can see here the number, it says 11 by 2 doubles, right? That would be 11 solutions. Okay, and then we can plot this kind of things. Okay, let's try to plot it. I think, oh, so many solutions. Which one is the one? Maybe this guy. You can see that, correct? So this is all the kind of frontiers. Okay, so I hope that, again, I will upload this code. You can take a look and trying to see how to locate or find the non-dominating solution, right? The method is pretty simple. You just, gradually, change the weight, right? And then you can get all the non-dominated solutions. Okay. Let's say, I think, do we have another demo? For example, here, I don't know what is this one. Let me just trying to run. Oh, it's very slow. Just a second. Okay, let's run this code. I don't know what happened. Okay, that's something like this. What is this? Okay, anyway, so I think that you already get some sense of the code, right? We're trying to, by changing the weight, we can get different solutions in the frontier, right? So I will upload the commented code so that you can take a look. Again, that will be the, the whole lecture for today. So for the lecture on Wednesday, so we will kind of review all the kind of codes and all the kind of methods we have covered in this kind of a whole semester. Okay, that will be the kind of review for the exam 2. Again, exam 2 will be kind of cumulative, which means that everything will be included. Okay, I will talk more details on Wednesday. Okay, so for today, that will be all for today. Okay, so that's it, everybody. So have a wonderful day. Okay. Okay, cool. Thank you, everybody. Okay, you too, guys. I will upload the kind of a link to it. Bye-bye.